A very good morning. Today I am going to discuss about vector group test on transformers. But before proceeding to the conduction of the test, let me first recall related to the various vector groups associated with three-phase transformers. The vector group of transformer is an essential property for successful parallel operation of the transformers. Hence, every electrical power transformer must undergo through the vector group test of transformer at factory site to ensure the customer specified vector group of the transformer. Because if suppose the phase sequence or the order in which the phase will reach their maximum positive voltage is not identical for the two parallel transformer, then during each and every cycle each pair of the phase will be short circuited. So, it is indeed requirement for the engineer to determine the vector group of the transformers which needs to be connected in parallel to match with the demand when it is more than the capacity of the transformer. So, in case of the three-phase transformer, as we all know that the secondary and primary windings are normally connected with in various strategies like the star, delta or the zigzag. So, several secondary connections are available in respect of various primary three-phase connection in three-phase transformer. So, for same primary applied three-phase voltage, there may be the different three-phase secondary voltage with various magnitudes and phases for different internal connection of the transformer. So, normally the secondary voltages of three-phase transformer may undergo a phase shift of either 30-degree lead, 30-degree lag, 0-degree or 180-degree reversal with respect to line or phase to neutral voltages. So, when you are referring the nameplate ratings of the transformer, you always come across with the vector groups. So, here I have shown three photographs of three different transformers. The one is make of the Voltem transformer, the other is make of ABB and third one is a make of Cotson's Private Limited. So, from the photographs you can see that the first transformer has a vector group of DYN11, the center transformer has the vector group of again DYN11, but the third transformer consists the vector group of YND1. So, on the nameplate of three-phase transformer, the vector group is always mentioned. Typical representation of vector group could be YD1 or DY1, etc. In the vector group representation, the capital letter, the first capital letter always indicates the primary connection and the second small letter always indicates the secondary connection. Whereas, the third numerical figure conveys or always shows the angle of phase shift which is based on the clock convection. So, based on the clock convection, normally the three-phase transformers are categorized or grouped in four major categories. One is group 1 which shows 0 clock, it means 0-degree, group 2 6 o'clock, it means 180-degree, group 3 1 o'clock, it means minus 30-degree, group 4 11 o'clock plus 30-degree. So, if we are referring the clock, then minute hand is used to represent the primary phase to neutral voltage and always shown to occupy the position 12, whereas the hour hand represents the secondary phase to neutral voltage and may depending upon the phase shift and occupy the position other than 12 as you can see in the figure. So, I have shown the four figures. One is of 0 o'clock or the 12 o'clock, second is 6 o'clock, third is 1 o'clock and fourth is 11 o'clock. So, as the vectors are always rotating in anti-clockwise, so when the clock shows 1 o'clock, then it can be known as there is a 30-degree lag in a secondary voltage with respect to the primary voltage, and if it is 11 o'clock, then it represents 30-degree lead. So, you can refer the reference which I have mentioned for getting more details regarding the vector groups, and from the same website I have taken this table. So, the left side shows the phase shift and right side shows the connection. So, for 0 degree y 0, dd 0, dz 0, 30-degree lag yd1, dy1, yz1, likewise 30-degree lead yd11, dy11, yz11. So, for 0 degree and 180-degree phase shift, the transformers from the same group can only be allowed to connect them in parallel, but the vector group of 30-degree lag means yd1, dy1 or yz1 can be connected in parallel with the group of yd11, dy11 or yz11 only by interchanging the connections to obtain the similar group. Otherwise, as I have said that if the phase sequence is not matching, then it will create the dead short circuit during each and every reversal of the cycles. So, it will be very dangerous. So, we need to take care of this when we want to perform the parallel operation or when we try to connect the transformers in parallel. So, first we need to conduct the vector group test. So, let me see how the connections can be done to obtain the various groups. Consider the clock notation 0. So, 0 degree, I want to obtain y 0, dd 0 and dz 0. Okay, so, star can be vectorally represented like this. Now, as it is a 3-phase transformer, so we have 3 coils and 1 neutral wire. So, A1 A2 represents one coil, B1 B2 represents other coil, C1 C2 represents third coil. To obtain the star connection, connect A2 B2 C2 and neutral. So, we obtain the star connection. If we are making the same connection at the secondary side, then we will obtain y 0. It means there is no phase displacement between the secondary voltage and the primary voltage. dd 0, so it is represented as equilateral triangle. 3 coils A1, B1, C1, neutral is not present. To obtain delta connection, connect A2 with B1, B2 with C1 and C2 with A1. If we are again making the same connection at the secondary side, we will obtain dd0 vector group, dz0. So, delta is obtained by connecting A2 with B1, B2 with C1 and C2 with A1, and Z stands for the zigzag. So, the secondary side is connected in series with the other coils of the same circuit. So, zigzag transformer, the new concept is there. So, zigzag transformer is a special purpose transformer used in the power system, which is also called as interconnected star winding. So, zigzag transformer, as you can see in the photograph, that it has 6 coils in which 3 are outer coils and 3 are inner coils. The outer coil windings are called as zig winding and inner coil windings are known as zag winding. The zig winding of one phase is connected in series with zag winding of another phase. That is why it is called as interconnected star winding. So, how the coils are connected? The coil A1 is connected with coil C3, coil B1 is connected with coil A3, coil C1 is connected with coil B3. So, in each phase 2 coil windings will have the same number of turns, but they are wounded in opposite direction to cancel out the mismatch voltages. So, you can see that the dot representations are opposite to each other. Okay. The benefit of this is If we are making such kind of connection, then it will help us in eliminating the DC magnetizing component produced due to improper firing angles through the power electronic switches like SERs. So, if we are making the reversal connections, then the DC magnetizing component can be cancelled in each limb of zigzag transformer. The another advantage that we are getting is the harmonic voltage presented in the system to some extent can be cancelled by such winding due to its opposite connections. The another application of having zigzag transformer is as it offers the low impedance path to zero sequence component under fault condition. So, it can be perfectly used as earthing transformer with and earthing reference. If earthing current has to be limited under faulty condition, a suitable resistor can be placed in zigzag neutral terminal. The zigzag transformer is also used as a grounding transformer in a delta connected system where the neutral is not available, or in 3-wire system where again the neutral is not available. So, zigzag transformer is used for earthing of delta connected transformer. So, the advantages that we are getting from the zigzag connection is it is less costlier than the squat connection. It provides low impedance to zero sequence current. It eliminates harmonic voltages and it provides the perfect isolation between ground and the component. So, harmonic voltage suppression can be done by using this zigzag connection. The other connections are YY6, DD6 and DZ6. Okay, so YY6, so star, I think it is clear to you. The 6 can be achieved by reversing the connection. So, in previously we are sorting the terminals opposite to the dot marking, but to achieve the 180 degree out of phase, the terminals close to that dot terminals are sorted. So, it will give you the YY6. DD6. So, DD6 can be obtained by reversing the connection at the secondary of the delta connected transformer. So, A1 is connected with B2 terminal, B1 is connected with C2 and C1 is connected with A2. So, it will give you the DD6. Similarly, DZ6 you can also done by interchanging the connection at the secondary side. The another one is YD1, DY1 and YZ1. To obtain YD1 group, the delta secondary is connected by connecting A2 terminal with B1, B2 terminal with C1 and C2 terminal with A1. DY1 can be obtained by changing the connection at delta side. So, A1 is connected with B2, B1 is connected with C2 and C1 is connected with A2. So, you will obtain DY1 group. Similarly, YZ1, YD11. So, 11 group can be obtained by interchanging the position of the connections of YD1, DY1 or YZ1. So, to obtain YD11, the connection required at secondary side is A1 to B2, B1 to C2, C1 to A2. DY11 at primary side, the connections are A2 to B1, B2 to C1, C2 to A1. And for the YZ, interchange of the connections are required to obtain the required group. So, I think now we are able to conduct the vector group test on DY11, and it is more important when we want to connect 2 3-phase transformers in parallel. So, identification of the vector group of a given transformer ideally satisfied or gained by measuring the voltages. So, let me see how we can perform the test and what sort of the relationships we can obtain which conforms the particular vector group of a given transformer. So, let me take the example of DY11. Here I have represented the star connection marked with 2U, 2V, 2W and 2N terminal, and delta with 1U, 1V, 1W. So, D capital D represents the primary and Y and small letters represents the secondary. And numerical value 11 indicates the phase displacement. So dy and 11, it means that the secondary line voltage of a transformer will lead the primary voltage by an angle of 30 degree. So now I am rotating this vector to obtain 30 degree of phase shift. I am imposing it on delta. Okay. So here you can see that when you want to perform the test, sort the terminals 1U of primary with 2U of secondary and measure the voltage across the each of the terminals by applying the 3 phase 400 volt 50 hertz supply at the primary of the transformer. So measure the voltage across 1W 2W, then across 1W 2V. So you will get the one relationship, that is the voltage across the terminals primary of 1W to the secondary of 2V terminal is more than the voltage of or voltage across the 1W terminal of primary and 2W terminal of secondary. The another voltage is required to be measured across the terminals 1U of primary with neutral of secondary, and second is 1V of primary with neutral of secondary side. So vector sum of this voltage is equals to the voltage across the 1U terminal and 1V terminal of primary side. It means line to line voltage. The other voltages are measured across 1U terminal of primary with respect to 2W terminal of secondary and 1U terminal of primary and 2V terminal of secondary. Both the voltages are same. So once we are achieving this relationship, the available vector group is dy and 11. Similar practice can also be done if the vector group is supposed to be y and d 11. So star connected primary and delta connected secondary. 11, it means 30 degree of shifting towards the anti-clockwise direction. It will be imposed on the primary side. So short the 1U 2W and across the primary give 3 phase 400 volt 50 hertz supply and measure the voltage across 2U terminal of secondary with the 1N terminal of primary. So it will give the phase voltage which is greater than the voltage across 2V terminal of secondary, 1N terminal of primary, which is further greater than the voltage across 2W of primary and 1N terminal of 2W terminal of secondary and 1N terminal of primary. So that is the one relationship which you can obtain. The other voltages are measured across the terminal of 2V secondary with respect to 1W primary, then voltage across 2W and 1W, and third the voltage across 2V and 1V. So relationship obtained is the voltage across terminals 2V and 1W is more than the voltage across terminals 2W, 1W or 2V, 1V. So likewise you can conduct the test on any of the transformers and conforms the vector group. After conforming the vector group, it will allow you to connect the transformers in parallel only when the vector groups are similar. So if we are considering the 4 major groups, out of these 4 major groups, the group 1 which has the 0 degree phase displacement, and group 3 which group 2 which has a 180 degree phase displacement. These transformers can only be connected in parallel with those groups only. It means that the DD0 can be connected in parallel with the transformer which has the 0 degree phase displacement, whereas the dy6 can be connected in parallel with the transformer which has 180 degree phase shift, whereas for the group 3 and group 4 means dy1 and dy11 can be connected in parallel after interchanging the connections to obtain the similar vector groups. So, once the vector groups are found to be similar, it will allow us to connect the two transformers in parallel, so that we can avoid the effect of short circuiting during the reversal of each of the phases. So, guys, thank you. If you have any kind of the doubt, you can write me on my blog without any hesitation, and we will have a small kind of the discussion over there, where we can discuss a lot and eliminate the queries which may arising in your mind. So, thank you.